Hi, good afternoon everyone. Welcome to UTA Planetarium's next live star stream. I'm your astronomer, Levent Gürdemir. Today we are going to talk about a different subject. If you recall from last week, we talked about the telescopes and the astronomies, observatories, and how astronomers are using those observatories to conduct science. All right, so got a few questions in the meantime. And you asked, while we have observatories on the ground, and those are good observatories, why do we need telescopes in space? So to understand this, we need to look at this last picture one more time. So let's take a look at the last picture of our presentation from last week, because that was showing great images from what we are getting from space to the Earth. All right, so here is the image. So we have observatories right here, and if you remember, regardless how high you locate your telescope, yes, you are getting closer to the stars by locating higher telescope, but the problem is, regardless, you have this layer of air above your observatory. So air is a little problem if you are doing science in astronomy. And what is that problem? Air absorbs waves. Air doesn't absorb not any kind of wave. Air absorbs most of the waves, but allowing through two types of waves. And one type of is called optical waves. What are optical waves? Optical waves are the light we see from like green through blue. And on the other side, there is a radio waves coming from space. Air is also allowing them. So
I just need to butt in for a moment and let everyone know that, sorry to cover your face there, Levent. The university is testing their alarm system. So if you hear the alarms go off during the show, don't panic. Everything's okay here. They're just tests.
So in other words, don't be alarmed if you are hearing alarms over here. So there is nothing going wrong. All right, so in the radio section, radio signals coming from the sky, from the space. But don't mix up with the sound waves. We don't hear anything from space with those radio waves. The waves we hear, the sound is completely different type of wave. Radio waves are pretty much the waves coming to your radio. Or
wait, can you get FM radio in space? I really have no idea what the answer to this question is.
Yes.
Huh.
Yes.
What about this may be a little more tough. What about Sirius satellite radio?
Yes. Yeah, you get many type of waves from space, but the only thing you don't get is the a radio signal transmitted from the public radio station of an alien civilization. We haven't heard that yet.
Actually, is that why we use radio waves and those optical pathways to transmit TV and radio. I mean, I'm saying radio, but I mean like you listen to in your car radio. Is it because it's easy to pass through the air? That's why we use those wavelengths.
Absolutely, because we are trying to, especially in the long-range communication, if we are trying to broadcast our TV signals, we want them to go as far as possible, right? So that's why we are picking the frequencies that air is most transparent. And the radio astronomy actually not started until somebody was trying to do over-Atlantic communication, transatlantic communication. So let me tell you an interesting story. An engineer called Karl Jansky was working at the Bell Laboratories, Bell Communication. Bell was a big company in the United States, by the way. They had the most infrastructure at one point to make the phone communication possible. So he was working as an engineer, and they were working on a transatlantic communication, which somebody is in Europe and somebody is in the United States. They were trying to make a radio phone call with each other. But the problem was they were getting a static noise into their receivers. So where is that static coming from? They couldn't get it off in any ways. And then they realized that the one engineer, Karl Jansky, realized that actually static noise was coming from space. So like signals coming from space, is somebody trying to communicate with us? But it turns out what he discovered was cosmic microwave background signal, which is coming from the universe itself. And that is actually the proof, it later turned out to be proof for the Big Bang theory.
Wait, so I have to bring this up. This is a really neat fact that I've heard. Maybe you can confirm. I don't know. But way before we had digital TV, back when we had, UHF and VHF normal television that we used, analogs, maybe what they call it now. If you turned the TV on and you weren't tuned into a channel, you got white fuzzy stuff. I've heard that was the cosmic microwave background that you're picking up. That same noise that Jansky was able to. Can you confirm that? Have you heard this? Do you know what I'm talking about at all?
Well, I'm not exactly sure if that the white static is the cosmic microwave background, but it is certainly noticeable between the frequencies of 10 megahertz to 200 megahertz. Well, this covers the entire FM band. This covers the entire TV stations, and possibly right. So this noise is coming from the space, and if you don't filter it out, it's going to be in your broadcast.
Well, you heard it here first. You didn't already know it.
How about some other fun stuff with the radio signals? Could there be another type of signal that is actually transmitted from an intelligent life? Well, if you think about it, we started using the radio signals about 100 years ago. We started broadcasting our radio signals, radio stations or radio programs 100 years ago. Later than we started broadcasting TV signals too. So if that means if there is anybody listening us within the 100 light years away, that they must be receiving our first radio broadcasts. There will be a lot of probably tests, a lot of noises, but they will be the ones receiving them. So they will realize that I'm not sure how intelligent we are to them, but if they receive that
they'll find out
signals,
we make really bad TV, and yeah, it should be lots of drama. I think it should be a good time.
What is cool is actually if they can record, like let's say there's somebody listening 100 light years away, which is not far within the dimensions of the galaxy. So they are listening and they are recording the programs. So they will have the tapes of our first public radio broadcasts and public TV broadcasts. Even they can record the entire history within that 100 years if they could. Because signals will be just reaching out. So that would be cool. So what we are trying to do also, we also thought the opposite way. If they are they are broadcasting signals that intelligent life broadcasts some type of radio signals. Can we hear them? For that reason, a group of scientists formed another organization called SETI, Search for Extraterrestrial Intelligence organization, and they recently, I mean, they were using some other scientific telescopes, but it was getting even more and more difficult to get observation time, and finally I heard they funded their observatory, and those are their radio dishes, 100% of time dedicated to listen radio signals that may possibly coming from an intelligent life. Have they found any? That's a secret I'm not going to tell you. Of course
Maybe.
not.
No, we just got a comment from Kurt, and I have to agree with you. This is all I imagine, Kurt, is that the aliens do. The extraterrestrials, they pick up our radio signals and they see I Love Lucy or Saturday Night Live. I don't know which one will be worse for them, or better. Who knows?
And let's say hi to Kurt, because I remember him from last time.
Yes.
And for others also, if you have any questions, please use chat. I'm here and looking at the chat as I speak.
All right, so we made telescopes, Levent, that set on the ground. But as you mentioned before with your previous image, only so much of the electromagnetic spectrum could cut through the Earth's atmosphere. So our solution to this problem was?
Space.
How do we get them there? How do you get a telescope into outer space?
Well,
it's hard enough to build them on Earth.
If you throw it fast enough, it will eventually go into space.
That's one way.
That's one way of doing it, but it's not a practical way of doing it. Of course, space shuttles designed to carry such tasks. So they go launch in space, and then they carry the satellites in their cargo, and they release in the orbit. Everything is precisely calculated. Once the satellite is in the orbit, it starts orbiting around Earth.
Okay, so before we get to space, I think you mentioned this to me right before we started. We wanted to have a mediary between ground-based telescopes and space telescopes, and this one is especially close to home for us, right? So I'll transition these for us now so everybody can see it.
Yeah, that's a great observatory. Did you know that this is actually an observatory? Yes, you heard it right. This is an aircraft, Boeing 747, owned by NASA. And they installed a telescope on this telescope. This is this giant aircraft, and this is the door of the telescope. So this is a German-made 22.4 meter wide telescope, which is a large telescope. It is dedicated for infrared astronomy. So why it is on an aircraft, why it is not on the ground, and why it is not in space? Because the infrared signals, if we, Jim, can you show the very first signal image to us? Yeah, if you look at the infrared, some of the infrared waves can penetrate little bit in the air. So to observe, yes, here, like if you see, the majority of the air layer has been passed by infrared waves. Well, of course, you are on the ground, you are not receiving it, but if you are high enough, which is we are here at 10 kilometers, which is not a big deal for an aircraft to go, you can get most of the infrared light. So NASA thought that instead of sending another satellite in space, which is expensive, we can maybe put a telescope on an aircraft and fly that aircraft and do the observation. Great idea.
One big problem I know with telescopes is if there are vibrations, they can cause a telescope to not pick things up well. I can only imagine, I don't have a picture lined up for this, but that vibrations had to be a huge factor when they thought of this. Let's just cut a hole inside of a 747 and shove a telescope in there. That should work out great. We should have grabbed, I'll try to get a picture of this, but yes. Also, we have a professor here that worked on the telescope, right? do you want to relay what he said it was like being on there? We could bring him on in future episodes, as we've already had before.
Yeah, we need to do a dedicated Sophia. This aircraft is called Sophia, by the way. Let me first tell you from the engineering perspective, because I spoke to the engineers directly. This aircraft was modified by a company. I'm not sure if I'm allowed to mention its name, but I spoke to the engineers. And engineers said, well, when first this idea came on table, they said, no, this is no way, because this was not done before. Nobody thought about cutting a hole on the fuselage of an aircraft and putting a door and opening that door in the air. Because when you open the door, it changes all the aerodynamics, and an aircraft is mainly it's not designed for that, this type of aircraft. But I mean, they did it. They, of course, the engineers, if you ask them and justify it, and they will do anything for you. So they did it. And second, yes, Dr. Manfred Kunz of the physics department flew on the airplane. Actually, I was going to go too, but I had some personal valid reasons to not to go on that day, and I couldn't go.
I got this is the image of the telescope that is inside of the airplane. There's this huge structure built around it, outside of the regular. I don't know. Would you call this a rich accretion style setup? Something like that. But you can see that there's so much more than just the simple telescope attached in here.
Yeah, I mean, there are, like, moving mechanism is also, and aircraft flies significantly tilted in most of the time when it's observing, which is not comfortable to stay in the aircraft. So yeah, Dr. Kunz had that experience, and he shared his experience when he was back. He was certainly thrilled with the all observations and all the being in the aircraft in the stratosphere. So it takes a long time. It takes about 24 hours flying and observing and coming back. In the meantime, of course, there is no first seat class. You don't get good food service. Certainly, there are no alcoholic beverages that you can sip on during your flight. But it's a very different experience. So. This is one of the infrared observatories flying high. It's not in space, but it is flying high in the. This aircraft, by the way, when it's observing, it reaches up to like 40,000 feet. It is little above if you are going to Europe, aircrafts are usually going about 30 to 33,000 feet. So the 40,000 feet is going above that.
Okay, so it's time for us to do space telescopes, right?
Yes, let's go into space. We are still in the air.
Should we start with Spitzer?
Yes, let's start with Spitzer. I remember the launch of this telescope. I hope I'm not getting too old to remember all of these memories, because I remember from old people, they always say, oh, I remember the dedication of this building, and it was... Anyway, I mean, this telescope, Spitzer infrared telescope. So first of all, why do we need infrared telescope in space? If whatever we are trying to observe is not very hot object, like a star itself, for example, it is not going to show up optically. It is not going to show up in any other region, but it will just glow in infrared. Low temperature objects glow in infrared. Humans glow in infrared. How do you know humans glow in infrared? Like, have you ever seen the fireman's camera? The firemen's, they carry a special camera called infrared camera. So what they do is, if they are in the environment that they cannot see people, like it is either too dark or there's a smoke covered in the environment, so they use those cameras to find people, because people glow in infrared. Stardust also glows in infrared. Star formation, first, like the protostars and the dust accumulates, and all the beginning of the stages of the star formation glows in infrared. And if we are trying to detect the regions where the stars form, if there are planets around the stars, and if they are just maybe the planets forming, they glow in infrared. We need infrared telescope. So Spitzer. There's one challenge with the infrared observations. When they designed and launched the Spitzer, so the Spitzer is not just a satellite orbiting around Earth. So look at the orbit of Spitzer. So they put, like, Earth is over here. They launched Spitzer they call it Earth trailing orbit, which means the Spitzer is launched in an orbit to orbit around the sun. So Spitzer actually goes and orbits around the sun, but it's sharing the same orbit with Earth. Don't worry, it's not going to collide with Earth, but it is sharing the same orbit. And it is drifting away bit by bit, step by step from Earth. So scientists wanted Spitzer to be away from Earth. Do you know why? Because not only that, the heat, again, low temperature stuff glows in infrared. So you get a lot of infrared light from Earth itself. So you need to put your detector away from Earth so it cools down and gets away from all the noise coming from the Earth. So it should not go near any heat source. Of course, Spitzer is always pointed in the opposite direction from the sun, because again, we are not trying to get any heat from the sun, from Earth, from other planets. So that's why, that made Spitzer a little bit special. Unfortunately, I heard Spitzer instrument died back in June, so it is not operational anymore. And one more collection to space junk. It is going to be there, I don't know for how long. And
I think I saw that it had some malfunctions early on, or maybe not early on, but maybe a year ago, and then they were able to get it back online, and then it finally this year, like, actually ended its service in time. It's unfortunate, especially when you see its lifespan set next to Hubble, right?
Yeah. I mean, the satellites, there is only like an expectation of lifetime. Sometimes they fail prematurely. But eventually all satellites will fail because they are relying on batteries, even though they're like solar chargers. Every battery, remember, from your car, one day it will die. Once your power is out, battery is dead, the satellite is dead. Unlike Hubble, let's talk about this great engineering design. So Hubble Space Telescope was launched in 1990. Well, it has been in service for 31 crashing years. It is serviced 4 times, but it is in operation still today, and I don't want to jinx it because we love Hubble Space Telescope 31 years. Servicing something like this is not easy. The size of this is nearly a school bus. 2.4 meter telescope it has, but to service it, you cannot just say, hey, come back for a few minutes to the NASA garage and we are going to just change the oil and tires. And no, you cannot do that. So the space shuttle goes, captures this, astronauts go out, service it, and then they come back.
So right now we have no way for I guess NASA directly to service it at all. Something goes wrong with Hubble, it's dead in the water at this point.
Even a long time ago, they did the service mission number 4, and they said this is absolutely the last one we are doing it. Well, it's an old instrument, so it needs to be replaced. However, it was going to be replaced a decade ago, more than a decade ago. The first, we'll talk about James Webb Telescope, I hope.
Definitely. I have slides.
Yes.
We will definitely be talking about James Webb Space Telescope.
So this telescope, performs and operates mainly in optical range. Optical range means we look at and see what we see. But let's talk about the Hubble's importance first. So Hubble Space Telescope, yeah, took pictures. A lot of first it discovered the solar system, took great pictures of the planets, and they were amazing. Most of our scientists, they printed them out, laminated, and made great posters on our office walls. But this is the most significant image of the Hubble Space Telescope. This is called ultra deep field, which means Hubble looks at some point in the space. Optically, you look at it and you see nothing. It's darkness. So if you're interested in photography, you would know. So in dark, you take a picture and nothing comes out. But if you give enough exposure time, then you may start seeing some things in dark. So this is what the Hubble did.
In this photo, I see, and I know you're going to get to this galaxies, but how can you tell the stars? Are there stars in this photo that you can see?
No. This is Hubble Space Telescope was pointed away from the Milky Way galaxy, so there is no star in the picture. So everything, every light source you see in this picture is a galaxy. What we did say before Hubble, we said, oh, there may be just maybe a few hundred galaxies in space. A few hundred? In one picture, the Hubble is able to capture that many galaxies. So think about the number of stars in a galaxy. Well, finding the number of stars in a galaxy is a crazy thing because it is equal to the finding number of grain of sands on a beach. Imagine yourself trying to find the number of grain of sands on a beach and maybe counting like 1, 2, 3, 4, 5. It's not possible. So if you count it though, you will end up with a number like 200 billion stars. It is a very rough approximation. So 200 billion stars each. Do you have calculator? Can you just pull it out and maybe like try to calculate the first try writing 200 billion. You will find out how big of a number it is. And then multiply the number with that many galaxies and find the number of stars just located in this picture. Here is the challenge. You cannot do that. One more thing about the Hubble's ultra deep field image. So Einstein said, if light goes around a massive object, light will change its path. It will bend. Or let's say this way, massive objects will bend light. Here is a bent light, and here is a bent light, and you will find these type of bent curvatures in all over the place in the picture. What is there?
We got a question from
We don't
Kurt.
see. Yeah.
It says, I heard a measurement on the Hubble's lens was out of spec, and the intern that installed the lens tried to force it because it didn't fit right, and that was the reason it was blind at initial operation. That is so unfortunate that, I mean, I've certainly heard that before. I think most people have. When they first launched Hubble, it was like not working or not operational.
I don't remember what exactly, but this sounds like true. After they launched Hubble, they were waiting for the first great image, and it turned out a fuzzy, very poor image that you could even take a better picture with ground-based backyard telescope. So that was very disappointing. But
try to get a confirmation of what you said, Kurt. But I can't right now off the top of my head confirm exactly why it was out of whack.
Mm-hmm.
But I will search for that right now.
Yeah. That may be also related with some unforeseen space effect, because that was the first optical telescope in space. Anyway, we were talking about this bent light. Those are showing you the possible existence of a black hole in the picture. So every time you see that type of shape, it is called gravitational lensing, and around black holes that happens a lot. Okay. Next. So,
all right, let's go to the future.
Hubble is old. And of course, NASA knew about that. And in 1996, like 6 years after the launch of Hubble, NASA set the goal to put a better telescope in space. Isn't that nice? And they set the launch date as 2007. Isn't that nice?
Wait. It's 2021, Levent. We're like 14 years late.
Yes. James Webb Telescope has not been launched yet. Can you believe that? Good news is it is set to launch this Halloween, upcoming Halloween, October 31st. But this is the maybe 500th postponement of the James Webb Telescope. Yeah, in 2007, if you recall, the economy was not doing well in the United States, so the launch was postponed because of the budget issues, and then later budget issues did another postponement, and then whatever issues did another postponement, and in 2021 February we are still talking about the launch of James Webb Telescope. So it is much bigger than Hubble, much better designed than Hubble, 6.5 meter long mirrors, and if you recall from the last week's stream, the mirrors are not in a single piece. They are honeycombed pattern because it is easier and to deal with the large mirrors if they are in segmentational pattern, because every mirror, every segment can be controlled individually. So this telescope is going to be replacing the Hubble, but not replacing the place of Hubble. Hubble Space Telescope is just like other satellites. It orbits around Earth. So this telescope will be located in a different place. Jim, can you show us the placement of James Webb Telescope?
Of it, grabbing that real quick. There you go.
Here we go. So James Webb Telescope is going here. So what's the deal with here? Why we picked a point and marked it L2? There's a good reason for that. Look at it first. Earth, Moon. So it is about exceeding 3 times the distance of Earth and the Moon. This location is very far. And why we are trying to put the telescope far away? Remember the Spitzer? We are trying to isolate all the noise and heat coming from the Earth. So we want our telescope to be independent as much as possible.
I want to interrupt for just a second. Sorry a little bit, but this is not a scale model representation of the size of the Earth and distance relative to the Moon. So just that's an important point. We see that all the time, and the Moon is way farther away.
Yes, but the James Webb location is exceeding 3 times the Earth-Moon orbit.
Yeah, it's still way farther than the 250,000 miles that the Moon usually sits.
And if you are wondering what these L points are, so let's talk about this. Well, Earth has gravity. It pulls us on the planet. And the Sun also has gravity, and it pulls all the objects on us. So this is an equilibrium point. So that means if you put something over here, that object or that satellite will be in the balance of Earth's pull and the Sun's pull. So if we put a satellite over here, that means we don't have to give extra energy to keep the satellite in place. There is actually a satellite over here called SOHO, Solar Observatory, looking at the Sun all the time. So this is actually a free ride point for satellite. So, but this is not the only point. If you put a satellite in the point of L2, L3 is on the other side, L4 and L5, they are all equilibrium points by gravitational pull for satellites. So again, James Webb Telescope will be also in the gravitational equilibrium of the Earth and the Sun. So there will be a minimum energy required to operate or keep that telescope in that place.
All right.
Apparently, you cannot service that. If anything goes wrong, it will go wrong. And there is no turning point for that because, I mean, remember the challenge back in 1969. Going to this object from this was a big deal. Going from, and since early 70s, we stopped going to the moon. And we never been that far with all the space rockets and all the technology and everything we improved. We haven't been that far in the past 40 years. So going over here is not likely.
All right. So I have a question about Spitzer. Do you know if is Spitzer confirmed in L5, or was it whenever it was still working? Because I thought for some reason it was in some kind of Lagrange point.
Yeah, I don't know where the Spitzer was before it failed.
I'll get a source. We'll get a source and an answer on it.
Because it was drifting, it will stand on L5 point momentarily and it will just keep drifting because somebody has to stop it to remain stable at the L5 point. And L5 point is actually pretty far.
Extremely far, yeah. The number I don't even want to. Too big to type into chat. That's for sure.
We can calculate. This must be 60 degrees over here. So this distance is roughly 100 million kilometers. So you can do the geometry. Are there any fifth graders watching?
Kilometers, I think.
Any sixth graders watching? You can calculate this distance. I'm telling you how far this side is and what this angle is.
Some SOHCAHTOA, right?
It's easy math. For a college students, it is just under 1 minute.
Yeah. Okay. So we can see that James Webb's going to be the future. We should talk about what we expect to see from it relative to something we know, like the Hubble, right?
Yes, the bigger telescope is pretty much farther we see in space, and this diagram is showing with the ground-based observatories we were able to see that far. So this is pretty close in the universe because optical light is just get weakens and weakens, and if a galaxy is far away, the light and the waves never make it to the telescope. So after 1995, the first year the Hubble Deep Field image was taken, so we were able to see in the universe that far. So ultra deep field taken second time and third time, and this is the expectation of James Webb telescope. So let's take a look at it. Is nearly 200 million light years away. 200 million light years. How big is the universe? Well, the edge of the universe is at 14 billion light years away. Well, if you compare that, still James Webb is not going too far to see the edge of the universe. But it will give us a good clue what's up there.
Whew, long distance. All right, we've covered a lot of the wavelengths. It's time for X-ray, I think.
How about ultraviolet?
We did. I just skipped over ultraviolet.
Okay.
Hubble sees ultraviolet, right?
That's fine. Yeah, Hubble has ultraviolet instrument. And if we are interested in hotter stars, like OBA type stars, then we do our observations in ultraviolet cameras. Not a lot of ultraviolet reaches down Earth, fortunately, because there is little ultraviolet reaches down Earth, and that is making skin cancer.
That's why we have to wear sunblock, right?
You should better, because it is literally burning skin.
All right.
All right. So let's talk about X-rays.
We just got a question from Kurt right before we move on. Sorry. Good question. So he says the edge of the known universe. There may be more than beyond 14 billion.
It is about 14 billion, and 14 is rounding up. It was like 13.7, 13.8 billion light years away.
But could there be more, or is there calculations or something that say 14 is the only possible or most likely?
Well, we don't know what's beyond. What we can tell is the bubble of light since the Big Bang. So the way we calculate the edge of the universe is since the Big Bang, at the Big Bang, everything was at the pinpoint zero place. And then after the Big Bang, the universe started expanding. The light bubble is actually started expanding, or the light started expanding in a bubble. Well, we can measure how far the light has gone since the Big Bang, and it is 13.7, almost 14 billion light years ago. So this is what we call our universe. It's a bubble with a lot of photons, light carriers in it. What's beyond? We don't know, because we don't have access beyond the light bubble. There may be other light bubbles, other universes. Who knows? I mean, that's a great topic of cosmology, but currently we don't know what may be behind bubble, if there is anything.
All right, let's move to X-rays.
X-rays. So X-rays, you may be familiar with X-rays from the doctor's office. When you go, if you have potentially broken bone somewhere, so doctors take X-rays, because X-rays are blocking the X-ray light, X-ray stream, and everything else, all the muscles and everything else is transparent to the X-rays, so they can get a good picture of X-rays. It appears in shadows. But X-rays are dangerous. Even in the doctor's office, you get too close to the detector, and usually the doctor or the technician taking the X-ray go up behind a thick wall and wear some special protective gear. So we know X-rays are dangerous. And unfortunately, none of them are making down to the ground. Otherwise, we would just mutate every minute, every hour under the flux of X-rays. But the X-rays must be coming from, if they are coming from space, must be coming from highly energetic objects, or highly energetic the processes make X-rays. First, we detected X-rays in 1960s.
Is that enough energy?
Oh, that's a wonderful energy. But those are even making even higher energies that we'll talk about when we go into the gamma rays. So in 1960s, the scientists were wondering about if we are getting any X-ray waves from space. So they put a detector on board of a rocket, and they launched that rocket in space. And guess what? From the constellation Cygnus, they detected a strong X-ray radiation. So what could that be? That turned out to be the first discovered black hole. They named it Cygnus X1. X is the designation for X-ray. 1 is the first detected, and the Cygnus is the address, the constellation it's coming from. So Cygnus X1 was the first detected black hole. So if we are studying black holes, we need X-ray observatories. And the only way we can get X-ray waves is the space. These don't work in ground. So this is, again, another like a school bus size telescope.
Here's a fancy graphic to
Yes.
show the size of it. It is 45 feet long. That is humongous.
And it has special shields and everything. We are talking about NASA's Chandra X-ray Observatory. It has been in operation for many, many years, and it has doing great job. We have also a faculty member who gets data from this telescope and studies supernovas. So speaking about supernovas, would you like to go to the next one? The last one.
Last one.
Gamma rays.
Gamma rays.
Gamma rays are important rays because gamma rays are related with the cosmic rays. That is a big mystery. So again, we do not get any gamma rays on the ground. So we go into space. We actually do get some gamma rays when they are intense, because as you see, gamma rays are penetrating good amount to the air, to the level of like 10 kilometers. But if they are intense enough, some of them are reaching to the ground. And there are ground-based telescopes detecting these intense gamma ray bursts. But there are also space satellites observing the gamma rays. So we talked about black holes and very energetic processes to make X-rays. So if there is an even bigger process that makes even highly energetic particles that make gamma waves, those must be some sort of like explosions. And yes, supernova explosions that Jim showed a few times do make very highly energetic particles spreading into space, and we detect them in the forms of gamma waves. So if we are studying supernova explosions, then we work with these type of satellites.
We do have a telescope. There's a space telescope. This is the Compton Gamma Ray Space Telescope. So this studies gamma rays from space.
Mm-hmm. But the mystery is still the amount of cosmic ray we get as we speak doesn't explain the number of explosions we see, supernova explosions we see in the universe, because our estimation, given the observed number of explosions, we should have a lot less cosmic rays. But cosmic rays are raining down from the space as we speak. Fortunately, they are not interacting with us, so they are not killing us. They are completely just going from one side of Earth and others going out other side of Earth. But they are coming all the time, and we are detecting them with those observatories.
All right. Well, I think we ran out of questions. That does it for the show this week. Unless we have anything else, Levent.
Well, next week we will talk about Mars.
Oh,
the red planet.
Huge episode. You guys don't want to miss this one.
We would like to talk about Mars because in the following week we will do a special stream for the Mars Perseverance landing to just prepare the audience for the Perseverance landing. We would like to introduce Mars and why we interested in Mars, and we have a cool presentation for you, but you gotta wait for next week.
We have so much to bring up next week. We're tons of things, and then as he mentioned, don't forget we are doing a special live stream on the 18th. So on the 9th, February 9th, we'll have two cool things happening, but we're going to do the live stream and cover it on the 10th. We're good.
All right, everyone. Hope to see you next week. I will be here at the same time, same day.
All right. See you, everyone, next week.